Hi. Today we're going to tackle the concept of primary productivity, a rather important one in ecology. So let's get started. Now, the bottom line is this. Uh, Life on Earth is solar powered. Apart from a few organisms that live, say, in geothermal vents and geothermal pools, basically, apart from a few chemosynthetic organisms on the planet, the vast majority of life on the planet is solar powered. Now, let's talk a little bit about the sun. The sun is a medium-sized star. It is powered by the process, like all stars are, of thermonuclear fusion. So it's basically taking hydrogen atoms and turning them into helium atoms, just like a hydrogen bomb does on Earth. And you should take astronomy if you haven't taken it. It's an awesome class. But basically, the sun has been engaged in this process for about 5 billion years, and it's probably got about another 5 billion years worth of thermonuclear gas in its tank, if you will. All right. Now, what happens is the sun, it converts this thermonuclear, nuclear potential energy into heat in its core, and then that makes the sun's surface hot, and that hot surface sends light to Earth, and with that tiny amount of light that leaves the sun that hits the Earth. So, lots of energy leaves the sun, but a small fraction of it hits the Earth. And when it does hit the Earth, mostly what it does is it's just converted into heat. It makes the wind, it makes the weather, it causes the ocean currents and so on. We'll study that this year. I know I always say that, but we're going to study a lot of things, okay? Now, a small amount, like about 1% of it or so, is converted into food energy by plants. And thank God for that, because that's what we all depend on, okay? Now, let's just say this. All forms of energy can be measured in units called joules. I'm sure you use those in chemistry and biology. It can also be used in things like calories and kilocalories, but we'll mostly try to limit our discussion to joules, although I can't promise we always will. Now, all right, so if the sun is shining straight down on Earth, basically a square meter of the Earth's surface, with the sun's rays coming perpendicular to the surface, there's basically going to be 1,000 joules of energy per second hitting that surface. Now, 1 joule per second is what's known as a watt. I'm sure you've heard the term watt before. It's used a lot with electricity. A watt means that there's a conversion of 1 joule of energy per second. So what we find then is that sunlight hitting the Earth perpendicularly, if you mark out 1 square meter, what you're going to find is that each second, 1,000 joules of light energy are hitting the Earth's surface. So that basically gives us 1,000 watts per square meter, 1,000 joules per second per square meter, or in other words, 1 kilowatt per square meter. That's what happens. That's the maximum energy the sun can send to our planet. And I say maximum because what we find is that, well, if you change the angle of that light, it's gonna spread that light out, and that energy is no longer going to be confined to 1 square meter. So we find is that the density of light energy hitting the Earth's surface is always going to be greatest when it's coming straight down. And this is a good example. If I shine this flashlight straight down, that's the smallest I can get this column of light to be. If I tip this light at an angle, that light gets spread out over the same amount of energy coming out of the flashlight gets spread out over a larger area. And so therefore, there's less energy available for plants to photosynthesize if they're in this region than there is in this region, right? So here's another angle. My drawings are not that great, but here you go. Here I'm showing light come down at a 90-degree angle, hitting 1 meter. So this is, we're looking horizontally at their surface. So now we're looking down on it. It's 1 square meter. And the energy density is 1,000 watts per square meter, 1,000 joules per second per square meter. Now, if I took that and I shined that same light, instead of vertically down at a 90-degree angle, I shined it at a 30-degree angle. Well, then if we take the sine of 30 degrees, we're going to get 0.5. And so what that means then is basically we're going to take the area and say, well, 1 meter divided by 0.5, I'm spreading that light now over 2 meters. So instead of that light just landing here, it's going to get spread out over 2 meters. And so I'm going to have 2 square meters. And so my energy density is, I still have 1,000 watts of energy in this column of light, but it's spread out over 2 meters instead. So the energy density here is going to be half of what it was here. It's going to be 500 joules per second, or 500 watts instead of 1,000. So if I ever, this is something I'm going to ask you to do tomorrow. So I'm going to ask you to figure out how much energy strikes any given square meters of the Earth's surface. And basically, what you do is you take the maximum energy, 1,000 watts per square meter, and you simply multiply it by the sine of the angle of the sun in the sky. So here's my example. At noon on March 22, and I did look this up, the angle of the sunlight in Seoul is 52 degrees. We're going to learn how to do that later this year. Now, how many joules of light energy arrive each second on that square meter of surface at that time? All I have to do is take this number here, 1,000 watts per square meter, and multiply it by the sine of 52. And what I find then is I get 788 joules as opposed to the maximum of 1,000. So it's not that hard to do. All right? Why to do that? I don't know. Okay, so now here's the Earth. Here's the North Pole. Let's just say it's oriented this way. Here's the equator. What we find is this. The sun's rays tend to come in more perpendicular at the equator, and the same rays hitting the higher latitudes get spread out over a larger area. So there's a lower energy density closer to the poles, and the highest energy density is closer to the equator. Now, if you think in terms of biomes, where's our most productive terrestrial biomes? Well, it's at the equator. Why? Because there's more energy to work with. Where is it the lowest? Well, apart from deserts because of the limiting factor of water, it's low at the poles because light is so spread out. All right. Now, we did this with primary productivity. No, this is primary productivity. I do a lot of these in a day sometimes. I get confused. Okay, so let's just take a look at this. I know we did it yesterday we were talking about the carbon cycle. I get so mad at myself sometimes. All right, so if you recall from yesterday, the photosynthesis reaction is carbon dioxide plus water plus light energy makes basically sugar and oxygen. All right. Now, we call this, when this happens in plants and protists and bacteria, we call this productivity. So productivity is simply the capturing of light energy and conversion of it into stored energy. Now, let's just back off for a second and talk about two very important laws of physics. And these are easy ones to remember. The first law of thermodynamics simply tells us this: energy can never be created or destroyed. It can be changed from one form to another, from light to chemical potential energy, say in photosynthesis, or from nuclear potential energy into heat energy in the core of the sun, or heat energy to light energy at the surface of the sun. You can convert it from one form to another. You can transfer from one object, from the sun to the earth, but you can never invent it. You can never just create it. You can never make it go away. It's got to come from somewhere. It's got to go to somewhere. The second law of thermodynamics is this: that any time energy changes hands from one object to another, or changes forms from, say, light to chemical potential energy, you sort of have to pay a heat tax. Some of it is always lost or converted into heat energy. And if you remember, heat is just like randomly moving molecules, and most life forms can't take advantage of that. It's very difficult to turn heat energy into anything useful, so I often think it is lost. So it's going to be important as we move forward with the next few units to keep in mind that the second law of thermodynamics tells us that anytime we transfer energy, we're going to lose some of it to heat energy. There's that thing up there that I hate so much. Okay. So let's go back and look at this. The first law of thermodynamics tells us that during photosynthesis, this light energy captured from the sun has to go to somewhere. Where does it go? It goes into the sugar molecules that are produced during photosynthesis. All right. Now, so photosynthesis produces this compound, but this compound inside plants gets turned into a lot of other things. Okay, so we can link glucose together. All right, remember that we can basically hook it together and make starches. We can alter somewhat and turn it into lipids and so on. But basically, anytime we have carbon-carbon and carbon-hydrogen bonds, we're going to have a lot of chemical energy stored. So that's the process by which plants are taking in light energy and converting it to these other high energy things. Now, in order to power our bodies, what all organisms do, from plants to you and me to bacteria, we all do the same thing. We take sugar, we react it with oxygen, and then we turn it back into carbon dioxide, water, and we release the energy that was stored in it. So we can never end up with more energy coming out of here than we put into it. In fact, we get a little bit less because there's always some energy lost in this process, but lost to heat energy in this process. Okay, so the term primary productivity, this simply refers to the capturing of light energy and converting it into carbon compounds in plants. So photosynthetic organisms, protists, land plants, algae, basically these organisms engage in primary productivity by capturing sunlight and turning it into, let's just call it food energy, sugars, starches, lipids, things like that, that then fuel all the other organisms in an ecosystem. Now, gross primary productivity, or GPP, that is simply the rate at which this solar energy is captured and converted into sugars. So, in general, and I mentioned this earlier, only about 1.5% of the energy that hits a leaf, let's say, as light energy, is actually going to get converted into sugars. It takes time for plants to go through this process. So most of it just ends up as heat, but about 1.5% of it is going to get converted into to the energy stored in those sugars. So if we think about how we're going to measure the amount of GPP, well, if we think about it, it's amount of energy, which we measure in joules. I suppose we could also measure, if we wanted to, in kilocalories if we want, per square meter of photosynthetic surface per unit of time. Okay, so say per second. Although what we often find is it happens over a long period of time. So remember that these carbon compounds contain energy. So ecologists often kind of have a shortcut. We go, well, let's just do this. Let's measure, just a mass, say kilograms of living material. Right? We call it biomass per square meter. So instead of measuring the energy, we can kind of equate and say, well, there's X number of joules of energy present in a kilogram of biological material, and let's measure over a course of a year. So it's just an easier way. So basically, we have energy units, or the equivalent mass units associated with that biological compound, per square meter per unit of time. So I'm going to expand a little bit more on biomass here. So biomass is basically, if I take a plant and I dry it out and get rid of all the water. If I took a dead cow and I dried it out and all I have is just a cow, okay, with a dry cow with no water left in it. The mass I have, we call it biomass. It's got all these carbon compounds in them, and these carbon compounds can be reacted with oxygen, turned back into carbon dioxide and water, and release their energy. So basically, a mass of material is equivalent to a certain amount of energy, and it varies from organism to organism. But generally, we can say that 1 kilogram of biomass is roughly equivalent to 14 kilojoules of energy. That's not a hard, fast rule, but generally you could say that. Now, GPP, gross primary productivity, obviously it depends on light energy striking the surface. So you're going to have a lot less gross primary productivity near the poles than you are going to have at the equators. The tundra just doesn't produce as much of these chemicals as is produced at the equator. But there are other things that can limit it too. So nutrients. If you have an absence of nutrients, it's kind of hard to have productivity. In a desert, there's not much moisture, so you can't have much primary productivity. Also, animals, so your community interactions. If you have animals that are eating the plants, well, if you eat a leaf off a tree, if a deer eats a leaf off a tree, that leaf is not there anymore. It can't produce. Or how about this? You eat half a leaf, you have half as much productivity there. That might make even more sense. Now, net primary productivity is basically, think of it this way. A plant takes in a certain amount of energy, but it's also got to use some of its own energy to live. And remember, the second law of thermodynamics says that you're going to end up losing some of your energy to heat. And that's why we end up what we call net primary productivity. So basically what we do is we take the GPP, the total amount of sugars that are captured by an organism, and then we subtract the amount lost to respiration. So here's how much energy that the plant captured minus the amount it used in order to live on its own. Okay, so now under ideal conditions, what we find is GPP is going to be about 1.5% of the solar energy it lands on if we don't have any other limiting factors. But NPP is going to be about 1% because we're about 0.5% of it, about 33% of what was captured, if you will, is going to get lost to respiration. So basically, NPP and GPP are both measured in units of either energy per square meter per time or biomass per square meter per time. All right, so basically it's a simple equation. It's just NPP equals GPP minus energy loss through respiration. And I think I just said this, so I'm going to move on from here. Now, here's a table, and different people are going to use different units. So this author here used kilocalories per square meter per year, but it still is fairly accurate. And basically, this is it's worth looking at. I think we looked at this the other day when we were talking about biomes. If you look here, tropical rainforest, sun is coming straight down. We have maximum, 1,000 watts per square meter, right? So you have a lot of productivity as a result of that. Plus, there's also lots and lots of rain, so it's really easy for the plants to produce. But then if we look at, say, the savanna, where there's less, there's still plenty of light energy, but there's less water. So we have some limiting factors. Well, you can't produce as much. And look down here, I can go to a desert. So a desert, we don't have less than 200 as opposed to 9,000. That's just because, well, there's a really limiting factor of there's not much water. Now, if you look at, say, a deciduous forest versus a boreal forest, we're simply going up in latitude. Tropical rainforest, you're at the equator. Then deciduous temperate forest, you're basically halfway up to the poles. And then I get to a boreal forest, you're even closer to the poles. And then the polar tundra, even closer. But here we've got the limiting factor of permafrost. But the point is, less light energy is causing us to have less primary productivity. In this case, net productivity, because we're basically taking into account what the plants use. Now, I should point out, one way of measuring net primary productivity is just measure how much plant growth you get in a year, right? So, I had, 1 ton, a 1 ton tree at the beginning of this year, and then next year I had a 1.1 tree. Well, I got a 0.1 tons of net productivity. Here's another one I think is a pretty good way of looking at it. This is in grams per square meter per year. But again, you see that we get this pattern of the closer you are to the equator, the more productivity you have rather, and the farther you get from the equator and the closer you get to the pole, the less of it you have. Now, I'd like to talk a little bit about oceanic systems. So if you look here, we see that estuaries right here are actually very, very productive. They're quite productive, and some people would argue that these are almost as productive as tropical rainforests. And the reason is this: in the open ocean, you obviously don't have a limiting factor of water. Your limiting factor has to do with nutrients. Away from the shore, there isn't much in the way of nitrogen compounds, because when things die, they just sink to the bottom and carry their nitrogen with them. There's not a lot of phosphorus because phosphates tend to be insoluble in salt water, so they just aren't available. So we find is in the open ocean, it's almost like a dead area. The open Pacific just has very little life in it. All right, there's plenty of light, but not a lot of life. But as we move closer to the continents, what we call the continental shelves, so the shallow area just offshore from the continents, we tend to find quite a bit more productivity, and therefore you have more. There's more life. There's more biodiversity, and that's because nutrients come into the ocean from the rivers, and they make it a little bit out into the ocean, and so that area tends to have quite a bit of productivity because we no longer are limiting productivity by limiting the nutrients. Now, when we get into the estuaries, there's no dilution of these at all. It's just super high in nutrients, and these things have just explosive life in them because there's so much in the way of nutrients, and there's plenty of water, and there's plenty of light. So everything you need to grow, to capture sunlight, to have productivity is present in those estuaries. And then finally, another place we get a lot of gross primary productivity is where we get upwelling. So there are places we're going to talk about this year where wind patterns are such that they force cold, deep, nutrient-rich water up towards the surface of the continents. And when those come up, they bring all those nutrients with them. And, you've got light, you've got water, and now you've got nutrients, and you get a lot of productivity in that situation. And I think that's it for this one here. So see you guys tomorrow.